This is a video about the relationship between position as a function of time, velocity as a function of time, and acceleration as a function of time. And so what I'm doing here is move things around a little bit here. Um, I'm going to orient the x-axis vertically like this. So my x-axis is pointing up. And the problem I'm describing here is one where, let's say, the floor was right here, and on a ledge that was 5 meters above the floor, an object is thrown with an initial velocity, upward velocity of 20 meters per second. And there is acceleration acting, and the acceleration is acting downward. It has a value of minus 10 meters per second per second. So this is a pretty good approximation to what happens on the Earth if you ignore air resistance and you take 10 instead of 9.8. And so I've summarized the parameters up here. X naught is equal to 5 meters. That is, we're throwing it from an initial above the floor height of 5 meters. And it has an initial upward velocity of 20 meters per second. The acceleration is minus 10 meters per second, and we're going to think about these plots are generated over a time interval from 0 to 5 seconds, 0 seconds to 5 seconds. Okay, so the first thing to say is that if we start at the bottom, the slope of the v versus t curve is the acceleration. So the slope of this, I'll do it like that. The slope of the v versus t curve is the acceleration. All right, so this has a negative slope. This is a negative number. That's minus 10 in the middle here. The minus sign is truncated, but you can kind of see it above and below, so that's a minus 10. And in fact, if you look at the v versus t curve, you can see if I go over 1 second, I come down 10 meters per second. I go over another second, I come down another 10 meters per second, which means that the slope of this is minus 10 meters per second, and it is the acceleration. Okay, similarly, the slope of x versus t is v of t. And that's a little bit harder to see, but let me see if I can draw a line here. Let's take a red line, and let me draw a line from here down through there, and then I'll draw a black line across at zero slope like this. Okay. So you can see at the apex point for x versus t, and so remember x is pointing up, and so this point at t equals 2 seconds on the x versus t curve would be the apex position of this object at which we threw up in the air. And at that instant of time, it has 0 velocity, and you can see if you read down at the same instant of time, it has 0 velocity. But that 0 velocity corresponds with the slope of the curve here. And if you picked another point, for example, this point right here, and so let me do that again. Let me go over and we'll grab another red line here if I can. Let's see if I can do it at t equals 1. Like that. All right, so at t equals 1, the velocity has slope 10, and this, which is a positive number, and this has a positive slope, and the slope at t equals 1 on the x versus t curve is 10 meters per second. And so how do we define slope on a curve which is changing? Well, the answer to that is that what you do is you draw a tangent line. And so I will attempt to do that right here. Not very well. That's supposed to be a line right there, tangent to the curve, and the slope of this line is 10. If you go like at t equals 3, over on the other side here, and so t equals 3, if I do the same thing there, um, and so I didn't do a very good job there, but anyway, just to continue, there's a negative slope here. You can see this is starting to go down, and that corresponds to this being negative, and in fact, the slope of the tangent line here at t equals 3 on the x versus t curve is whatever the value at t equals 3 is on the v versus t curve. So it looks like it's minus 10. And again, we could draw a tangent line here, which would have a downward going slope like this. Okay, which would, the slope of this tangent line would be the v of 3, where 3 is the seconds. Okay, so that's the first point. The if you take any one of these curves, the slope of the curve underneath it the value of the curve underneath it is the slope of the curve above it. Okay. Now the second thing is that if you look at the area under v versus t, so for example, if you look at the area under the v versus t curve, and I will just kind of scratch this in here if I can. Let's see if I can here. I'll use a green color. And so from 0 to 1, the slope underneath the v versus t curve, which would be this area that I'm sketching in right there, this area. That's an area. And so this area has the units of meters. Because in order to find this area, this is the area of a trapezoid. In fact, what I could do is I could divide this into a rectangle and a triangle, but there's also a formula for the area of a trapezoid. To compute that area, I would use height data, which is in meters per second, and I would multiply by horizontal data, which is in meters. I'm sorry, in seconds. Meters per second times seconds is going to give me meters. So the area here is going to have the units of length. And so what I want to communicate is that the area under the v versus t curve between 0 and 1 is the displacement over the same time interval on the x versus t curve. And so if you look here, you can see that x starts at position 5, and it looks like at 1 second it's gotten to about 20, and so the displacement is 15 meters. That means that this area has to be 15 meters. So the area under the v versus t curve gives the displacement undergone by this object, not the position, the displacement. Remember, displacement is a change in position. You can say a similar thing for the area under the a versus t curve and the change in velocity. And that's not something we're going to focus on as much, and so I'll just maybe leave it where it is right here. All right, so to summarize, there's a slope relationship that I've sketched in here, and there is also an area under relationship. The primary one that we will use is going to be the area under the v versus t gives us the displacement.